Welcome to qnawire.
So now we'll work on problem 72 from chapter 17. This question tells us that we have a sample of pyridine which is being titrated with HCl, and we need to calculate the pH, several volumes of added acid, and then sketch the titration curve. So first, let's calculate how much initial moles of base we have at the beginning. So we do that by multiplying the concentration of base times the volume, and this is equal to 0.003125 moles of pyridine. So now let's go ahead and calculate the pH, initial pH when no volume of acid has been added. So we have a weak base, so we're going to need an ice table. So we have C5H5N plus H2O will produce the conjugate acid and hydroxide. So we have our ice. We have 0.125 for the initial concentration of pyridine, none for our products. So minus X, plus X, and plus X. So 0.125 minus X, X, and X are our equilibrium concentrations. So we set these equal to Kb, which is 1.7 times 10 to the minus 9 equals the products x squared over 0.125 minus x. We use our approximation that x is small to eliminate the minus x, and we get x is equal to 1.46 times 10 to the minus 5, and that's concentration of OH, so we can calculate POH as being equal to 4.84, and pH as being equal to 9.16 by subtracting 4.84 from 14. So let's move to the second part where it asks us to calculate after 10 milliliters of acid have been added. So here we can do another ice table since we are not past the first equivalence point, or the equivalence point. So C5H5N plus HCl will produce the conjugate acid So we have our initial concentration, or here we'll use moles since we're going to be subtracting the amount of reactant, 3125. We have 0.001 moles of acid based on the volume times the concentration. And so our change will be, of course, complete reaction of the acid. Which leaves us with 0.00215 and 0.001 and 0.001. So we have a buffer, so we can do the Henderson-Hasselbalch equation where POH is equal to the pKa, which is 8.77, plus the log of the base over the acid. So this here is equal to 8.44. And if we calculate pH, it's equal to 5.56. So already a dramatic drop. So now let's go ahead and do 20 milliliters on the bottom here. So I'm going to use the equations, the symbols from up here to calculate. And so all that we've done here is we've added another 0.001 moles of acid. So we subtract from the initial 0.002 to get equilibrium moles of 0.001125. So this should have been 2125, just for clarity. The calculation is correct. And 0.002 for both of these substances. So this is our equilibrium for after 20 milliliters. So again, we use the analog of the Henderson-Hasselbalch equation to calculate pOH. So this time we have 0.002 over 0.001125, which is equal to 9.02. And when we convert to pH, it's equal to 4.98. So the next point that we'll work on is at equivalence. So at equivalence, we need to look for the volume of acid, which we're looking for, because we're going to need that for the titration plot at the end. And so we get that from dividing the number of moles of the initial base that we had, 0.003125, divided by the concentration of acid, which is 0.100 molar. And we get this is equal to 0.03125 liters, or 31.25 milliliters. And so at this point, we need to calculate the concentration of the conjugate acid. So the concentration of C5, H5, NH plus is equal to the number of moles. So everything that was pyridine at the beginning is now the conjugate acid. And we divide by the total volume, which is this plus the initial volume. So we get 0.05625, which is equal to 0.056 molar. So this is our concentration here. So what we need to do is we need to draw an ice table where we set this as the initial concentration of the conjugate acid and then calculate X. So since we're familiar with the ice tables, as we've done several in this problem, I'll just simply write it as Ka is equal to the Ka for the conjugate acid of pyridine over X squared divided by 0.056 minus X. So we solve for X, and X is equal to 5.74 times 10 to the minus 4 molar, and pH is equal to 3.24. So that's for the equivalence point. Now at half the equivalence point, to calculate the volume of half the equivalence point, all we need to do is divide the volume of the equivalence divided by 2, which is 31.25 divided by 2 gives us 15.63 milliliters. And then the pH here is based on the fact that we're at half equivalence. So the pOH is equal to pKb, which is equal to 8.77. And so we can calculate pH as being equal to 5.23 at half equivalence. So the next point it asks us to calculate is at 40 milliliters. At this point, we're a certain amount of moles beyond the equivalence point. So let's go ahead and calculate the total moles here in 40 milliliters total. So moles HCl is equal to 0.1 molar times the volume, which is 0.040 liters, which is equal to 0.04 moles. So now we need to calculate the amount of excess HCl. Excess HCl will be the amount of moles that we have minus the amount of moles of base we had at the beginning. So this value is 8.75 times 10 to the minus 4 moles. And so we calculate our hydrogen ion concentration by dividing 8.75 times 10 to the minus 4 by now what we have as the total volume, which is 0.065 liters. And this is equal to 0.013 molar. And if we calculate pH by taking the negative log, we get 1.87. So the last point which we're asked to calculate is the pH at 50 milliliters added acid. So we'll do this the same way that we did 40 milliliters. So we'll add the excess HCl, we'll calculate. In the previous problem, we had an excess of 8.75 times 10 to the minus 4. And we've added 10 milliliters more since 40. So that would be an extra plus 0.001 moles. And we add both of these together and we get 0.001875 moles of HCl. So what we need to do is calculate the hydrogen ion concentration as being equal to 0.001875 moles divided by what is now our total volume, which is 0.075 liters. And this is equal to 0.025 molar. And we can calculate the pH by taking the negative log of this value as being 1.60. So now all that's left to do is plot our titration curve. So first let's draw our axes. So we have pH and volume of acid. We're going to go up to 50 milliliters. So we have 25 about halfway here. And then we will also have about 10 and 20 here. This is roughly drawn to scale. 30 and 40. We can draw our pH scale from 0 to 14. 7 in the middle, 11, and 3. So our initial pH is 9.16. So let's draw our point in red around here, roughly. And then at 10 milliliters, the pH drops fairly rapidly to 5.56. So this is because the reason we have such a drop it rapidly before the equivalence point, number one, dilution, but also due to the fact that pyridine is such a weak base that the conjugate acid is actually stronger. So we have a strong drop in pH here. quickly. And our pH at 20 milliliters is 4.98, so just slightly below here. And then at equivalence, we have a volume of 31.25 and a pH of 3.24. So about here. Then we can put in our half equivalence where we have a pH at 15.63 milliliters. pH of 5.23 at 15.63, so roughly here. Then at 40 milliliters, it drops to 1.87, so about here. And 1.6 is about here at 50 milliliters. So we can draw our curve here. So we have this rapid decrease at first, and then it sort of slows down, smooths out as we would expect from a buffered solution. It goes through these points here, and then we have our equivalence at 31.25 milliliters, so we have a slight decrease here. This probably could be better drawn with a sharper decline. So let me do that. Like this. And so probably here as well. So obviously it's not going to be perfect if we're drawing by hand, so don't stress it too much, but this is roughly what the titration